We've introduced our basic angular quantities, the angular displacement, the angular velocity, the angular acceleration. However, within each object, each point also has a linear quantity. As the object is rotating around, each point within the object, for instance, has a speed. Or you may want to consider a car maybe driving around the Saluda traffic circle. Well, the car has an angular velocity, but if you glance down at the speedometer, you're seeing in essence the regular linear velocity. And it seems reasonable that maybe there's a connection between angular and linear quantities. That's what we're going to look at here. We actually already have one. If we draw a circle, not too bad, and consider the radius we had and our angular displacement delta theta and this arc length delta s, we had, as long as we used radians, that the delta s would equal the radius times the central angle. I also said that anytime we use this equation, the angle measure must be in radians. Well, if we go just a little bit further, let's consider a circle and a point that's going around the circle. Now this point could be a single point within a larger object, potato-shaped object, or it could be the car going around the Saluda traffic circle. We're just focusing on one point as it's going around, and let the center of the circle be the axis of rotation. Still, we have the radius r, and this point has a speed, although here I'm going to call this, I'm going to give it a subscript. This is v sub t, not t for time, but actually t for tangential. Let's just kind of figure out what the v is first. If we go back to the first picture and we look at the delta s, that's close, even though it's an arc length, as long as it's not too great a distance, that's close to being the displacement of the object. And displacement divided by elapsed time is just the average velocity. So if we do the displacement, try again. If we do the displacement divided by the elapsed time, except maybe to make the math a little bit better, I kind of want this to be the velocity. Still haven't exactly explained why it's a subscript of t, but we'll see that in just a moment. But technically, if I really want this to be the instantaneous velocity, I would do the limit for this quantity. In any case, we have the limit as the delta t goes to 0, and the delta s from up above was equal to r delta theta, and then divided by the elapsed time. The r is not changing in time. It can be pulled out front. So we have r times the limit delta t goes to 0, and if dealing with the limit really just doesn't suit you, it's really not something that you need right here. It's just making the math a little more formal. We have the delta theta over delta t, but that limit was just the angular velocity, so this ends up being r omega. So the linear velocity for a point within a rotating object is just equal to the radius of the circle, in essence, or the distance to the axis of rotation, times the angular velocity. And let's see, we'll probably summarize these equations in just a moment, so I'm not going to over highlight this. Now if we go back up to the picture and extend, or really let's draw in a coordinate system that's compatible with this motion. It's a tilted coordinate system, kind of like being on the incline. And then the axis here that includes the radius of the circle, that's the radial axis. And the axis that includes the velocity itself, so that is here, is the tangential axis, because it is tangent to the circle. And the velocity lies within the tangential axis, so the velocity is entirely tangential when you have a rotation around a fixed axis. So now, to summarize very quickly, we have the delta S, back in black, summary, here we go, that the delta S, which is very similar to the linear displacement, is r times the angular displacement. And then we also have the tangential velocity is r times the angular velocity. Both of these equations, if they're going to be used in this form, require radians. Now the next logical step is to consider the angular acceleration and the linear acceleration, but those are a little more complicated, which isn't to say that we aren't going to do them, but it is to say that we're going to save that for the next section.